All right, so we've talked about enolates in a lot of different ways. We've talked about a lot of different reactions. In the last video, we started to talk about kinetic versus thermodynamic enolates, and so how we can control kind of which enolate we make and all of that. There's one more class of enolates that I want to talk about. These are actually, from the enolate standpoint, are much easier. These are much more synthetically useful. We use these to make other compounds and that kind of stuff. And that's we're going to talk about an alpha position that's between two carbonyls. And so, why is that different and all of that we'll get into a little bit, but we'll also mostly focus on how do we use these positions. If we have a position between two carbonyls, one, why does that change the reactivity? And it doesn't really, but also what can we do with that once we have identified that we have that position? And so an enolate between two carbonyls, so these are going to be 1,3 dicarbonyls that we're going to be talking about. Um, we'll just stick with a simple one for now. So if you have this 2,5-butane dione, right, we have carbonyls at carbon 2, or 2,4, excuse me, 2,4-butane dione. We have carbonyls at carbon 2 and carbon 4. They are 3 carbons apart. This is a 1,3 dicarbonyl. And if we treat this with a base, I'm just going to use sodium hydroxide. We're not going to make this too difficult. When we have this, we have a bunch of different alpha positions, right? This position is an alpha position, this position is an alpha position, and this one is also an alpha position. So we have 3 options for where we can remove the hydrogen from. And now you might be tempted to say, well, sodium hydroxide, I know from previous videos, was going to make the thermodynamic enolate, so I'm going to take the hydrogen from the most substitute carbon, etc., etc. And that is not going to be correct here. Instead, what we're going to look at is where is the most, remember that the thermodynamic conditions, we find where is the most stable conjugate base, right? And the most stable conjugate base is going to be the base that has the most resonance possibilities. And so if we remove this hydrogen from in between these two carbonyls, right? We make an enolate, of course, because that's what we're doing here. Well, we make an enolate that is now going to be stabilized by additional resonance forms. So we have our enolate. We can draw 2 other resonance forms. We can draw an enolate where we put the negative charge on the carbon, the alpha carbon, right? Not the most stable resonance structure because negative charge on carbon is rarely a good idea. But we can also draw a resonance form where we put the negative charge on the other oxygen. All of these are resonance structures of the same enolate, right? All of these are enolates. They're all the same enolate, just drawn 3 different ways. But the point is we can distribute this negative charge throughout, and that makes this position very, very stable, this negative charge very stable. And so the take-home message here is that when you have carbonyls in a 1,3 rearrangement, 1,3 dicarbonyls form enolates at the alpha position between the carbonyls. And they do this almost exclusively. It doesn't really matter what base you use or anything. Because this hydrogen is the most acidic hydrogen, this is the hydrogen that will always be removed, right? So if you see this pattern, this 1,3 dicarbonyl pattern, the hydrogen that's going to be removed when we treat it with base is always going to be the hydrogen in between those 2 carbonyls.